wanted to share the same that I discussed with the class and to post the same.
Okay.
So I suggest that we have the quizzes on 13th of September,
Give me a minute. Let me look at my calendar. 13th of September works fine. Yes.
11th of October,
11th of October works fine again.
and 8th of November.
Okay. Perfectly fine.
Yes, but the only request is that we can't have them during the tutorial slot because many students have group wise tutorials for other courses as well in the slot that we have. So it will be recommended if we can have them in the class slot itself to avoid
No,
any
but
clash.
then the date will change. No? Monday we don't have class, right?
Monday we don't have a class.
No, so see, our normal classes are on Tuesday, Wednesdays, and Fridays. No?
Got it. So we might have to shift them to the next day in that case, the ones that I've suggested.
Okay, so you are trying to say is that the closest, so you wanted to host it in the class hours, like on
Class
Tuesdays.
hours, so that because it does not clash with other students out there.
No, I'm fine. I am fine anyway. So then what you could do is you can just send the dates email to me,
Okay, sir.
and we can do that. So you can so Monday of course we don't have a class, no. So in that way you
Right,
can.
I'll shift it one day after.
So you can just send me an email and we can. So which means that the first quiz would be on 14th of September.
Right, sir.
That should be okay. Yeah, so that could be done, yes. And regarding the tute, Thursday won't work. So what we should do is, okay, we will use the Saturday slot for the tute, and we will keep the Friday slot for the doubt clearing session, or the other way around. Anything is fine for me. Friday we can have for the tute and Saturday for doubt clearing. So you can also send me a confirmation.
Right, so you can keep the tutorial earlier and probably after that asking doubts would make more sense. So Friday you can have the tutor and Saturday the doubt clearing session.
Okay, perfect. So yeah, so this just to again, so we'll have our tutor on Friday to everyone, and Saturday we'll open up the doubt clearing session. I am fine with that.
Sure, sir.
Okay, so yeah,
Yes.
yeah. So this thanks for this what you call scheduling thing. So any other questions related to our class? Something is not clear? Anything that require more discussion in the class, or anyone?
Hello, sir.
Yes.
So yesterday you gave an example of YouTube manometer.
Uh-huh.
Uh, so I did not understand that example. That how is it related with that second order system?
Give me a minute. Give me a minute. Just give me a minute. So just give me a minute. I'm just trying to search for a material that which I can show you. Just give me a minute. Okay, so the meanwhile that gets opened. Give me a second. I think yeah, I'll be able to open it right now. So any other questions other than this? Uh, okay. Meanwhile, I'll share my screen anyway, just to save time. Yeah. So we'll talk about this how YouTube manometer thing in due course. So meanwhile, so again, so the same slide is with here. So we are looking for systems that has different characteristics. The simplest, of course, is first order, which essentially mean that their underlying model is like model is first order ODE. Okay. Uh, or essentially, the other argument is the Laplace transform, which is the transfer function. The denominator transfer function is of the order of one. So either of these things. Okay, give me a minute. Now I think I'll be able to show the YouTube manometer thing. Just give me a minute. Okay, so let me share my screen here. So, could you guys see my screen?
Yes.
So see, so whatever you see as 11A1 is a YouTube manometer, correct? Hello, am I audible?
Yes, sir.
Okay, so let's say you have this, of course it has two legs, leg 1 and leg 2, and you would put some fluid inside that, okay? And let's say then you figure out a, what you call, some initial reference, which is shown as this dotted line over here. You see that? And from and from that in a reference line, you tend to model the height of the liquid above or below that. Fine. So now when things are at rest, so you see the left meniscus and the right meniscus, both of them would stay static. And let's say now maybe from you use some instrument, okay, and blow air to either of these legs, leg 1 or leg 2, whichever side you would like to. So then what would happen? The air would compress the fluid, rather push the fluid down. Let's say we are doing it from leg 1. The air would push the fluid down on the leg 1. As a result, the leg 2 level will also go up. You're only going to give a step, what I would say, step input, which means that no, you are just going to give a what you call pulse input. You just put some level of pressure over here, then you take it off. Huh? Then you remove the air pressure line. But let's say when you put the pressure inside, as you would really see, the fluid in the leg 1 would come down and fluid in the leg 2 would go up. Fine. Then you take off the pressure also, so you would really see that the fluid in this legs, both the legs would keep on oscillating across this reference line. If you keep a reference line H, if you figure out the height of the fluid from a reference line, which is, let's say it is H, okay, so then even if you take out the pressure, what would happen is this fluid would keep on oscillating in this column, and finally it would become, after some time, what I would say, when the pressure, when the overall, due to various levels of friction, the applied pressure become nullified, it would again come to a stationary position. So during that time, when you plot the height, which is from a reference point in the YouTube manometer as a function of time, you would really see that it would also tend to oscillate something like this. Let me check for an example here. Something like this. So see, when you, let's say if you are looking for a height, it would go up, then it come down. So then by that time, some of the, so see, due to friction, that pressure would keep on decreasing. Then the next round it would go less up, then less down, and finally it would, the overall, what I would say, the liquid in the both legs would settle. So this is an example of second order system. Why it is become second order system? Okay, so when you try to derive the transfer function, you would really see that it, or when you try to derive the ODE, so how do you derive the ODE? So we have seen in the tank system, you will have to do a force balance. Similarly, here also you will have to do the overall force balance, pressure applied in leg 1 minus pressure applied in the leg 2, due to some force due to the difference in pressure. If there is a friction, you add, would be the mass times acceleration. Rate of change of force would be mass times acceleration. And you may, and you, if so whatever, so you substitute what is the pressure in the leg 1, leg 2, okay, then the force due to the gas. And if you, let's say if you are going to neglect friction whatsoever, eventually you would, it would result in a differential equation as in the form of equation 11a6. Just apply it, you substitute it, and when you simplified, or it would eventually result in a differential equation, either 11a5 or 11a6, both are same. Then you really see that, then again when you apply Laplace transform, you would really see that it is going into a clean second order system. Is this clear now?
Yes, sir.
Okay, so any questions related to this? Is this okay? So then I think let us continue if there are no more questions. So we will continue with the second order systems. So that's why it's a second order system. So again, so YouTube manometer is a second order system which is underdamped. Why it is underdamped? You see the height, okay, so height versus time, okay, from a reference line, you would see that it would keep on oscillating and finally getting converged. So which essentially means that the your system is oscillatory, which essentially means that your theta value is less than 1, which essentially means that it is an underdamped system. And why? So that's why it is called. It is mostly physical related. So you are not, unlike two first order system connected in series. Here you are not doing anything. You are not constructing a system. So it's the normal system. You just operated it. So it is mostly coming from their original operation, which is physics governed. Okay. So we have, so see, we have now, so we have seen the first order system, various inputs which are step, okay, ramp, and sinusoidal. So similarly for second order system also, we'll have to now look at what is the, so because these three are the standard inputs that you would really apply. So we would like to see how it is, so we would like to see how it is responding to these three input. Again, for step response. Okay, so what is our y of s? Y of s by u of s is equal to k by tau square s square plus 2 zeta tau s plus 1, and us is a step here, so us would become ut us become m by s, where m is the magnitude of the steps, which essentially means that you are going from here to here. This magnitude is, this is u, this is with respect to time, this magnitude is m. Okay, so then what will you get you as your y of s? You have to just multiply k times m by s into 1 by tau square s square plus 2 zeta s plus 1. So now what is that? So unlike your other first order system, so when we take the inverse of it, okay. So here three different condition would arise. So we are not going into the derivation here. So you can, if you need, you can take a look at least the step response which is shown uh, in the textbook. What eventually is going to happen. So this, unlike your first order system, the additional parameter that you have over here, which is theta, would play a key role in terms of deciding the process characteristics. So in the first order systems, if it is a step response, you will get only one response. Okay. So while here, depending upon the value of the theta, three different conditions would arise as we see it. One, of course, as in overdamped system. One is critically damped. That would be very close to the first order system output, because it is like two first order system without what you call any damping. And third is the underdamped system, which means essentially an oscillatory system. So if you look at the underdamped system, starting from this, which we are talking about right now also, so you would really say that your output is oscillatory with respect to a set input. So the simplest way to visualize this is, okay, you would have some sine or cosine terms in the response. So to characterize this oscillatory response, okay, and it is a high, it's highly a function of zeta, because the zeta, the effect of the zeta would be will determine what is the level of oscillation it has. But how do you get this expression again? So you will have to just take again an inverse Laplace. Okay, so you have to write it separately, a by s, then b by whatever, and c by whatever. So factorize this and write it in as partial fraction. Again, take an inverse, but make sure that your theta value is less than 1. So when you factorize, the denominator, you have to accommodate the fact that your zeta is less than 1. That's why it is leading into a very different expression. When it become underdamped, as you would really see, your output would contain a lot of sine and cosine terms. Why? Because underdamped response is characterized by oscillation. So to characterize that in the final output, it would be, it would have this, it would include sine and cosine terms. You don't need to by heart anything. It is there in your, what you call, in the Laplace table, how the response of the second order system works. So you only need to take a look at that. Okay. And when it becomes critically damped, so what does that mean? So when it becomes critically damped, your zeta value is equal to 1. So you don't have to look for the zeta here. Okay. So it would be much more simple. So Km by Km by s times, okay, it would be most likely tau s plus 1 the whole square. So the response of this would have very close resemblance with the first order system. Of course, it wouldn't be identical because there are two first order systems connected. So if you really look at the first order system response, except the fact that this 1 plus t by tau is there, it is very similar to that of first order system with a step response. Okay, and the last one is of course the overdamped system, which essentially means that your theta is greater than 1, and you would really see that it is also similar, but again you will have to account for the uh, overdampedness, so the response would be looking like this. Again, no need to by heart this. You will be able to use your, what you call, reference books if something being asked. So so what you should qualitatively understand is that how these three category of responses are fundamentally different. So if you are looking for a second order system with an underdamped characteristics, you will have to understand that output would contain sinusoids, because otherwise the response would be oscillate, will not be able to capture the oscillatory response. Okay, and for the second order system with critically damped condition, so critically damped condition, so which essentially means that your output, okay, so this is the reference, it should be able to reach the, it would most likely look like a first order system. And let's say if it is an over damped system, the process become very slow. So see, if you look at the critically damped and the what you call the over damped system, you would see that the output has been quashed multiple levels by these terms like that. So which essentially means that your output response would be much slower compared to a critically damped system. Okay, so this is the theta value greater than 1. Okay, here it is theta equal to 1. Okay, and the third is of course the uh, under damped condition, which essentially means that the response would be oscillatory in nature. Finally it becomes it is. So any questions so far? And how do you get it? As I told you, take this Laplace transform, just take an inverse. But again, when, so the difference that you need to kind of you probably need to take a more closer look here is, here your zeta is also coming into the system, so your roots would be a function of zeta. So that's why three different categories of results emerge when they become 1, when zeta become 1, when zeta is greater than 1, zeta is less than 1, which essentially means that, so these are the three roots that you would really need to deal with it. When zeta greater than 1, it would be real and unequal roots. When zeta is less equal to 1, it becomes real and equal roots. And when zeta is less than 1, it would be complex conjugates. So again, roots of what? Denominator polynomial. Any questions here? Anything that require more clarification? Okay, so this is something that more pictorial representation, how y by km, which is the normalized response, and t by tau, which is the normalized time. So if you look at the expression, everything would be y is equal to km. So y by km would be a normalized response, and t would be t by tau, which is the normalized time. So you plot them against. So what you would really see that if the zeta value is smaller, the level of oscillation is very high. So if you see, and if the zeta value keep on increasing, of course, then we are moving from the under damped to slowly to critically damped condition. So when zeta become 2 minus 0.2, you see a lot of oscillation, and you would see a progressive decrease in the oscillation when the value of zeta is increasing. So at 0.8, this is more or less. So you see that there is the oscillation is more or less damped. It's pretty clean. Still there is some oscillation, but it's much better. And when you see the other extreme, which is the zeta value equal to 1 to greater than 1. Equal to 1 is as if it would highly resemble like a first order system. Then what is happening? So again, when you increase the zeta, so okay, the oscillations are decreasing, but your process is also getting sluggish. Your process has become slow. So zeta is equal to 1 is the ideal case, no oscillation and fast. Here you see that lot of oscillation and process would settle only after a long time. So this oscillation keep on. So zeta, though this oscillations technically are not desirable, right? Because which essentially means that your system keep on vibrating, be it a reactor, be it a manometer, be it an automotive vehicle. So the ideal response that you could think of is zeta is equal to 1. So if you are somewhere here, you tend to move towards this line, and if you are here, you tend to move down to this line, which this may be the best possible case. This could be your zeta is equal to 1. And how do you do that? So as I told, underdamped systems are generally a physics related. You could think of, for instance, if it is a U-tube manometer wherein water is the fluid, and you would see it is getting oscillated, and that is what we have seen. So can someone tell us in some way to decrease the oscillation of such system? There are multiple ways you could do it physically. Can someone say what are some intuitive ways of reducing the oscillation, which essentially means that you are moving from underdamped character to critically damped character to overdamped character? Can someone think and tell? Hello, are you all there? Yeah. So just think how to. So for instance, you are given with a YouTube manometer, and you are given with all freedom to manipulate. And with the current YouTube manometer, with water being the fluid, you can do any change. Feel free to do any change, even though that is not easy to do. But hypothetically, you are given all sort of freedom to play with the YouTube manometer, and you found that at the moment the water is being the fluid. Okay, now you see it's a highly underdamped and system, and you have been asked to move from underdamped to critically damped or to overdamped because you really wanted to reduce the oscillation. What will you do? Tell me one or two options. Just think about it, what all things you could do. Any feedback? Any thoughts? One option is you can change from water to more dense liquid, for instance mercury. So because of the inertia in the mercury, you would see that there would be lesser oscillation because it's more heavier fluid. Agreed or not agreed?
Yes, sir.
Okay, so let's say your manometer wall is thin. You can consider making a thick wall, which is not thick wall in the sense your cross section would be large. So initially your manometer is, let's say this is D and this is D prime, and you would make D prime much larger than D. Then what would happen? The oscillation would decrease or increase? let's say you pour water to two tanks, one having smaller cross section with another having, let's say you pour a bucket of water here and you do the same thing over here. Which one will have more oscillation? At A or B? Because the meniscus would keep on oscillating if you add more water to it. A or B? Anyway, I think please.
So B would have less oscillation.
Yeah, so the same logic applies here. So you have increased the number of, you have increased the cross-sectional area here. So which essentially means that, it essentially means more capacity. More capacity. More capacity means that even if you add more water or when you put pressure, because of the high capacity, which is essentially result in more inertia. More capacity means more mass. Again, that would result in more inertia. It's easier. It's not. It would be easier to push a what you call smaller object compared to a larger object. So here, this would also reduce the oscillation. So by doing so, these are some means. I'm saying this is just as example. So you could physically think of many other means. How to convert your work, what you call over-damped case, under-damped case to over-damped case. Why? So another typical example is what you call automobiles. So let's say your automobile, so vehicle that you would going to travel in a highway. If the vehicle is lighter, which means maybe 1000 cc, 800 cc kind of a vehicle, it would tend to vibrate a lot. You would see when you drive in an expressway, you would feel the difference. It would tend to oscillate a lot. And let's say if you are driving in a heavy vehicle, for instance, 1500 cc, let's say an SUV. Other one, you assume that it's a small hatchback car. So you would see that the oscillation, the overall vibration is much lesser if you are going for a heavier SUV. The same reason. So this is fun. So what is happening? You are moving from an underdamped case to an overdamped case or a critically damped case, or you might have just reduced the underdampedness. So either by what you call increasing the overall capacity, overall density. So here you increase the weight. The same principle applies here. So these are like I'm trying to connect you with the physics. So if you really need to change this character, you have to go back and do something really in the system itself. So any questions here? Okay, so now let's summarize what you have told. The responses exhibit high degree of oscillation and overshoot. So there is a character called overshoot. See, you are interested to retain, let's say, y by km, normalized response. 0 to 1 could be the maximum that you wanted. But when due to the presence of this oscillation, it has going beyond 1, then finally it settles at 1. And so it is this particular thing, which is the undesirable excess response. This one. This is basically the overshoot of the system, because you really wanted to be here, but your system, due to its inherent characteristic, ran away from the original point that you really needed to have it here. And while the other way around, the larger value would result in slow response, and it would take a lot of time to converge. And as I told, the what I would say, the middle ground is theta 1, which is the fastest and with lesser overshoot, which is the critically damped case. So there are various characteristics of second order underdamped system. You can specify some of the properties. Basically, So this is the response that you would really see for a second order underdamped system, which means that it goes out. So this is something that you need to, this is your target, but it went ahead and came down and oscillates and finally settled. So if you given such a output profile, so there are various parameters defined for underdamped system. One is rise time. Rise time is the time taken to reach the steady state value. So you really wanted to be here in this allot. So let me just draw this. This was your aspiration. You wanted to be here near the red line, but due to the underdampedness, it went above and then keep on oscillating. So the time taken to reach the first, to touch this red line is called the rise time, ER. And so rise time is not the settling time. Rise time, because the system overshoots, then keep on oscillating, and finally after a long time it will settle. Okay, so then what happens is it goes and reaches its first peak, and there are multiple such peaks before it becomes settles. Okay, then similar to the rise time, there is also property called time to reach first peak, which is TP. When it is the time taken, so this is time versus output, the time taken to reach that first peak. Okay, so then settling time. So this finally, so eventually your process tend to, after a long time, slowly would settle, and it would remain inside a small band with 5% difference compared to the final output. So 5 percentage. So even let's say your output, so your y by km value is 1. So it would tend to be between 1.05 and 0.95, and eventually it would, after a long time, this all would decay. But if, you can say when it becomes this band of 5% above and 5% below, you could say that the process is settled. Finally, the ultimate settlement would take, what I would say, asymptotic. It will take a long time because there would be minor oscillation here and there. But if it is just between this bands, 95% above or below, then you call it as the time taken for that, which is the settling time. Okay, so then we will define the overshoot. So you have this peak. Okay, the peak would go all the way up and down, and let A be the distance between the steady state value to the peak, and B be the distance between starting value to the steady state value. Then overshoot is defined as A by B. What is the, how much percentage it overshoot compared to the steady state value? And also there is something known as decay ratio. So what is decay ratio? Decay ratio is, so your response keep on decaying, you see, it would keep on decaying. So, and which essentially means that the first peak height, second peak height would be much lesser than the first peak height. So decay ratio, which means that how much is the process decay, will be this, which is the ratio of C by A, where C is the height of the second peak and A is the height of the first peak. So what is the level of process decay which is obtained, that could be computed using C by A, and of course the period of oscillation. Period of oscillation is the time between two successive peaks. Then you would have the next peak here. So they are all most likely going to be the same. So these are certain characteristics that defines an underdamped second order process. So you have a rise time, then you will have a time to reach first peak, then there is a settling time, then there is an overshoot, decay ratio, and finally period of oscillation. So any questions at the moment?
No, sir.
Okay, so now why are we defining this? So if you look at So if you look at a response, and when you plot it, you will be able to calculate all of these parameters. So you only need a graph. If you plot, let's say you are sitting, let's say you are doing an experiment in the lab. Okay, you took a stopwatch and started noting H versus time for the YouTube manometer, or even height versus flow rate for the tank, and you collected all of this information and you plotted it. And so these are directly coming from, there is no expression used in calculating all of this. These are all coming from the data. You see that? Once you plot this, you will be able to calculate what is A by B, what is C by A, what is TR, what is TP and TS. Now, there are expressions that connect you with this and your zeta, which is your damping factor. So for instance, so if you compute the time to, and also tau also, which is the time constant and zeta. So when you get your time to reach the first peak, so this is officially computed, whether you can compute, so this is the expression for the time to reach first peak. Okay. And this is the expression for overshoot. And this is the expression for decay ratio, and this is the expression for period. So what I am trying to say is, let's say you plotted this graphs, okay, and you computed the overshoot, which is basically A by B, or decay ratio, which is C by A. And you know these numbers on the left hand side because this is coming from the graph, A by B or C by A. And you see this is just a function of zeta here, because pi you know and exponential. So if you know the decay ratio or overshoot, you will be able to calculate the value of zeta by inverting the expression. Similarly, if you once you get your theta, you should be able to again substitute either zeta in the expression for period or time to reach first peak, because you will be able to get the time to reach first peak from here, or computing the period from here. Okay, so what is unknown? You got it. So you used overshoot or decay ratio to compute zeta. Then once you have the zeta ready, you plug in over here. The only parameter that is unknown to you is tau. So you should be able to get that tau back. So then your model is simple: tau square x square plus s square plus 2 zeta tau s plus 1. So you should be able to get your system output back, or the model structure back, by just looking at the graphical profile and equating with the standard expression. So when you plot this and evaluate this experimentally, of course, when you do a numerical computation to calculate the period and so on and so forth, you should be able to relate them with the expression for the original expression for that. That would help you to backtrack and compute the values of the damping factor and time constant. Okay, so what we have seen was second order system with step response. You can also have a sinusoidal response. Again, so the details are skipped for brevity, and only so we would see that after the exponential terms have disappeared. Everywhere when you have the exponential term, and so it would be always a negative of exponential. So when the time become large, or t by tau become larger, so this term would eventually contribute much lesser. So then the output for this particular case, after the exponential terms are resolved, it would also be a sinusoidal expression. You would see this expression in the textbook, and it would be a sin omega t plus phi form, where phi would be computed like this. So numerical derivation is omitted for brevity, and you can also plot them and see. And this is a polar plot between omega tau versus a by k, which is your y by k. So with this, I think we would stop. And if you have any issues, I think we can discuss that in the doubt clearing class, or I think hopefully you should be able to get more idea how to use them when we solve the examples in tutorial. So any questions at the moment? If things are okay? Any questions?
No, sir. No, sir.
So I would strongly recommend for you to please review the material. So that we can have an engaging session. Otherwise, it would be like speaking on one side, and I don't have any clear sense how much you got it. So okay, more than that. So I don't have any clear sense on what how much you got, but I think, and also it's good to have interactive so that you will also feel more engaged in the class. So my sincere request, I am uploading my note much beforehand. Either you review beforehand or even just after the class, and come a bit more prepared so that we can have more engaging sessions. Okay, if there are no more comments, I think we shall close the class for now, and we'll continue this from Friday. Okay. Any questions, or we are okay? Hello. Okay then. Let's see you in the next class. Bye.
Thank you, sir.